Let's next see some problems on the mean value theorem. Let's start with number 4, where you consider this function square root of x minus 1 on the closed interval 1, 3. Note that the function is continuous on this closed interval and differentiable in its interior, open interval 1, 3. So you can apply the mean value theorem to it, which tells you that this quantity f of 3 minus f of 1 divided by 3 minus 1 equals the derivative of the function at some point c in the interior of this interval. We already know that, but our job here is to find those values of c for which this will be true. The theorem tells you that at least one such c exists, but there may be more than one. So we need to find them all. So we start the solution by taking any c in the interior of that interval 1, 3, that means in the open interval 1, 3, for which this condition is true. Now f of 3 is square root of 2 and f of 1 is 0. So we get this as the left hand side. If you differentiate square root of x minus 1 with respect to x, you get 1 divided by 2 times square root of x minus 1. When you evaluate that at c, this is what you get. And then after some simple algebra, you find that this is the only value of c, 3 divided by 2. Next, let us see number 8. Does the following function satisfy the hypothesis of the mean value theorem in the given interval? The function is this partly defined function f of x equals sin x divided by x if x is greater than or equal to minus pi and less than 0, and is defined to be equal to 0 when x is equal to 0. So the interval here is the closed interval minus pi, 0. And the answer obviously is no, which you can guess from this and this. Since we know that the limit of this ratio sin x divided by x as x approaches 0 is 1, so the left hand limit is also 1, which means that the left hand limit of our function at 0 is equal to 1, which however is not equal to the value of the function at 0, and that's why the function is not continuous at that single point x equal to 0. Remember that for all the hypotheses of the mean value theorem to be true, we need continuity throughout the closed interval. That's not happening here. And one more thing, because 0 is the right endpoint of the domain, so we can only talk about left continuity there. That's why this one-sided limit. Let's see one theory problem next, number 16. It took 14 seconds for a thermometer to rise from minus 90 degrees Celsius to 100 degrees Celsius when it was taken from a freezer and placed in boiling water. Show that along the way, somewhere, the mercury was rising exactly at this rate, 8.5 degrees Celsius per second. This is an application of the mean value theorem again. I will just give you a small hint and leave the rest to you. This is the hint. Note that 100 minus 19 divided by 14 is 8.5. Let's see another one, number 18, where we have to prove that for any two real numbers a and b, not necessarily distinct, the absolute value of sin b minus sin a is less than or equal to the absolute value of b minus a. Solution: the claim is obvious if a is equal to b. Since it's not given that a and b have to be different, they can be equal also. And in this case, this side as well as this side are both equal to 0. So we get equality, which is included in this inequality. So next we assume this, let a be not equal to b, and assume without loss of generality that a is less than b. You do understand that the other case where b is less than a need not be checked separately because of the presence of absolute value. Now what are we going to do in this case? We consider the sine function. Because the sine function is differentiable everywhere and continuous everywhere, in particular, it's also continuous in this closed interval a comma b and differentiable in the open interval a comma b. So by the mean value theorem, there exists a point C in this open interval such that sin b minus sin a divided by b minus a equals the derivative of sin at the point C, which just means that sin b minus sin a equals b minus a times the derivative, which is cosine of C. And now we consider the absolute value of sin b minus sin a, which equals the absolute value of this product, but then that equals the product of the individual absolute values. Now we know something about this, namely that this is less than or equal to 1. That is why this product is less than or equal to the absolute value of b minus a. So in this case also we are getting the inequality. So this completes the solution. In the next calculus video, we are going to start the next section, where we will say more about how we can use derivatives to say things about when a function is increasing, when it's decreasing. I mean, we saw something about that here in this section itself, but we want to be able to say more, and how that can help us spot exactly where a function has local maximum and local minimum.